Today we're going to talk about section 1.4 part 2, continuity on a closed interval, properties of continuity, and the intermediate value theorem. Yesterday we talked about continuity on an open interval where the endpoints were not included, but continuity in between those two unincluded endpoints meant there were no jumps, no holes, and no vertical asymptotes. Continuity on a closed interval is pretty much the same thing. The graph has to be continuous on the open interval from a to b, but also the limit of the function from the right of a has to equal that y value at a. So as we march across this function from the right of a, that y value right up here has to be f of a, has to be the same as the limit. So basically that means there can't be a hole there that's not filled in with the y value. And then x approaches b from the left, so x is approaching b from the left, the y value approaches that function value f of b. So the function value, the actual number you get when you plug in b, has to be the same as the limit. So there just is no hole there on the end. So the ends can't have holes, and the function in between has to have no jumps, no holes, or vertical asymptotes. So let's talk about the continuity of the function square root of 1 minus x squared. 1 minus x squared is inside of a square root, so we know it cannot be negative. It could be 0, it could be higher, but it can't be negative. So let's think about what values would make this greater than or equal to 0, because those are the values that do work. That is the place where this graph will be continuous. So if we subtract 1 from both sides, then we'll divide by negative 1. Remember, when you divide by negative with an inequality, you switch the inequality sign. So let's think about what x values, once you square them, will be less than or equal to 1. It would be values between negative 1 and 1. If you take the square root, you'd have that, but you got to think about the positive and negative values, positive and negative options, and in that you're going to have to switch the sign, positive and negative. So what that means is that x is between negative 1 and 1. So those are the values where this graph is continuous, between negative 1 and 1, including the endpoints. And that's all because it's under a square root, and you can't have a negative under a square root. On the AP test, they often have questions like this. Find a such that the function is continuous on the entire real line. Well, each part of that function is continuous itself. 2x cubed is the graph of 2x cubed, just a little steeper. Graph of x cubed a little bit steeper. But that's only for values equal to 3 and less than 3. So let's say this is 1, 2, there's 3. Something up there, and it's all these values here. But what about over here? So it's not going to keep going up. Over there we're going to have the piece ax. So this could be 2x, 3x, negative 4x, 1/2 x, we don't know. But it's some function times x, so it's going to be a straight line. It could be going this way, or it could be going that way. And we don't know how steep it's going to be. But it will go through the origin because there's no b value here in this y equals mx plus b. There's no y-intercept. This is for all x is greater than 3. So it could be this part from here on out, could be this part, but nothing over here. Nothing over here, okay? Well, for a graph to be continuous, it can't have any holes. Well, neither one of these has a hole in it. It can't have any vertical asymptotes. Neither one of these has a vertical asymptote. And it also can't have any jumps. The only way that these would have a jump is at x equals 3, because that's where the two parts are either going to match up or they're not. So we want to force them to match up. So what we're going to do, plug in 3 into that function, and you get 3 cubed. Oh, I don't know why. Did I say 3, 8? I don't know what I was thinking. Anyway, 3 cubed is 27 times 2 is 54. That's a pretty high y value. So this is the point 354. All right? We want this diagonal line, AX, to go through that point, to start there. Even though it's going to have an open circle there, we want it to go, well, it looks like it's going to go this way because it can't go down from there and still go through the origin because it has to have a y-intercept of 0. So it must be going this way, must have a positive slope. We want it to go through that point so that our graph curves up and then might have a sharp turn, which we call a cusp. And that's still continuous. But if it started at the point 360 or something up here, then it wouldn't be continuous. So we want to force this graph to hit the point 54 for its y value when x is 3. So we're going to plug 3 into here and set the two pieces equal. So you plug in the point where they could possibly break, where they could possibly have a jump, in for x, and then just set them equal to each other and solve for a. So I believe that's 18. So in this case, a is 18. Unless I did my math wrong. You can correct me tomorrow if I did. All right. Properties of continuity. B is a real number, so B is a constant. F and G are functions, and they're continuous at some point C. So if we've got two continuous functions and some real number, all of these things are true. What this is saying for the scalar multiple is that you can take any function that's continuous, like sine x, that's continuous, and multiply it by a number, and that will itself be continuous. Or you can take two functions that are continuous, like sine x and 3x, and add them together, and the answer will still be continuous at that point C. Or you can subtract two functions, or you can multiply two functions. As long as they're each individually continuous, the product of them will still be continuous at C. So there won't be a jump or a hole or a vertical asymptote at C. We can divide them too, as long as that denominator doesn't equal 0. So any continuous functions, you can pretty much do anything with them, and the answer will be continuous also. Polynomial functions are always continuous. A polynomial function is anything with decreasing exponents, so like 5x to the 4th minus 30x cubed plus 2x squared, blah, blah, blah. That's continuous everywhere. Rational functions are continuous everywhere as long as that denominator doesn't equal 0. Radical functions are continuous everywhere. Remember, if we have a cubed root of x, all values are in their domain, in their domains. All values of x are in there, but if we have an even function, then only positives and 0 are in the domain. So they're saying that as long as you stay within the domain of this function, the rest of it's continuous. Sine, cosine, tangent, cotangent, you know, sine and cosine both look like that, just shift it over. Tangent, cotangent, secant and cosecant are these U shapes. So we know there's asymptotes in between these, right? But for each piece that's in the domain, for each of these shapes, they're continuous. So if you could take any of these functions and do any of the previous things with them, like add, subtract, multiply, or divide them, they're still going to be continuous. So there's a lot of continuous functions. The other thing you can do with functions that are continuous, if you have two functions that are continuous, this one's continuous at the y value that you get when you plug in C, then you can do the composite function. So f of g of x, or written this way, f of g of x is continuous at C as long as when you plug in C to g, then the f function is continuous there. So tons of ways for continuous functions to create new continuous functions. Let's talk about the intervals on which each function is continuous. Tangent we know is sine over cosine. So really this is like a rational function. We do not want the denominator to equal 0. So where does cosine equal 0? Think about your unit circle. Cosine is 0 at pi over 2 and 3 pi over 2. And around, backwards and forwards. So if we want to show a pattern that goes on forever, we just pick a few values to show and put dots after. dot dot. Sorry, I can't fit that in there. So that's the interval on which each function is continuous. At least that's the interval on which tangent is continuous, from negative 3 pi over 2 to pi over 2, etc. Not including those endpoints, negative 3 pi over 2 and negative pi over 2, because the asymptote is right there. All right, how about the function sine of 1 over x, as long as x does not equal 0? But when x does equal 0, this function is going to equal 0. So since sine of 1 over x, this is continuous everywhere except at 0. And we know sine of x, if this were the composite function, sine is the outside function, 1 over x is the inside. We know sine of x is continuous everywhere. So then this should be continuous everywhere except at 0. So except at x equals 0, this function is continuous because 1 over x is the inside function, the g of x, and that only has a discontinuity at 0. And sine is continuous, so that's going to be continuous everywhere except at 0. So this one we could write like this: negative infinity to 0 and 0 to infinity. And since we're going to have this value here, then we can tell that this function is continuous. This function is continuous everywhere from negative infinity to 0. And this one is just the value at 0. It's not going to fill in our hole. So that's that one. It's kind of a weird looking graph. You can graph it if you want. And then x times sine x, that one's really weird. All right, this graph of x times sine of 1 over x, we can squeeze that between the absolute value graph. I drew that weird. So absolute value graph this way, positive absolute value of x, and the negative absolute value of x. So the negative absolute value of x is less than or equal to x times sine of 1 over x, which is less than or equal to the absolute value of x. So this is the graph of x times sine of 1 over x. It goes like this, crazy like that, and then it squeezes between there and like that. And so since these three graphs, this one's less than this one, which is less than or equal to this one, these are all less than or equal to each other, and the limit of h of x as x approaches 0 is 0, because the limit of this is 0 and the limit of this is 0, and since this one's less than this one, which is less than this one, then they all must have the same limit, so that must be 0. So that this part where x cannot equal 0, the 0 fills in that hole, so then that's a continuous graph. So this one's continuous everywhere. Now ours are not going to be that hard. They're going to be more like 1 over the square root of x minus 1. We'll decide where that's continuous. You have to think about where this part doesn't equal a negative, because it can't be a negative in a square root, and where the whole denominator can't be 0. So that must be, this would equal 0 when x equals 1, so x cannot equal 1. And then do we have to go higher than 1 or less than 1 to get numbers in here that are positive? Like higher than 1, right? We want x minus 1 to be greater than 1. Greater than 0. So that will be x is greater than 1. So x can't be 1, but it can be greater than 1. So our graph is continuous at every value from 1 up to infinity. So ours are going to be easier like that. I just wanted to show you a couple weird ones. This one is continuous everywhere except at 0, because we can't find two functions that we can squeeze this one between to have the limit equal 0. Like these can be, this one can be squeezed between these two, and then that fills in that place where we have a discontinuity. So won't be as hard as it looks. The intermediate value theorem we'll talk about in the next tape.